into a swimming pool, or tossed a wadded-up ball of paper into a trash can? To a physicist, both you and the paper wad are projectiles. This video explores how projectiles move through the air. In simple terms, a projectile is anything that is thrown, kicked, batted, or in some way propelled into the air. The path of a projectile is called its trajectory. To further simplify things, we'll ignore air resistance and treat all of our projectiles as ideal. Ideal projectiles are subject only to gravitational force during flight. As you will see, understanding why projectiles follow curving paths requires breaking the motion into component parts. After completing this assignment, you should be able to describe the motion at key points along a projectile's path, and explain why that path is parabolic. A solid understanding of vectors, one-dimensional motion, and free fall will help you get the most out of this video. Projectile motion is important because it allows you to solve motion problems in 2 dimensions. It is used to explain orbital motion, a topic you will learn about later, and because it explains many things happening around you. Now consider the simple experiment shown in the following video.
So here I am up on a 12-foot ladder. I have 2 bocce balls. What I'm going to do while I'm up here is I'm going to throw this bocce ball straight off to my side, while at the same time drop this bocce ball straight down. The question is, which ball hits the ground first? The one that I throw off to my side, the one that I let drop straight down, or they both hit at the same time? So as you can see, they both hit the ground at the same time.
Let's further explore the result by analyzing a nearly identical experiment. Imagine 2 people in a tower, much like the Leaning Tower of Pisa in Italy, except that it is not leaning. Each holds a baseball. At the same time, one person drops the ball to the ground, while the other throws it horizontally at high speed. As before, both balls strike the ground at the same time. The key to understanding this result is realizing that the curving path of the thrown ball, shown now in slow motion, is made up of a horizontal and a vertical component. More important, however, is the fact that these components are independent. That is, the horizontal motion does not affect the vertical motion. Let's compare the vertical motions of the 2 balls. To do so, we'll use motion diagrams of each ball. If we project the dots representing the vertical positions of the thrown ball back to the vertical axis, we see that they exactly match those of the drop ball. Is this a surprise? It should not be. 2 words explain the result. Free fall. Once released, whether dropped or thrown, each ball is subject only to the force due to gravity and thus is in free fall. Because all freely falling bodies accelerate at a constant rate of 9.8 meters per second squared, both balls strike the ground at the same time. Let's now look at the horizontal motion of the thrown ball. Projecting the horizontal positions down to the x-axis shows that they are equally spaced. This tells us that the horizontal acceleration is 0 and that the horizontal velocity is constant. It turns out that all projectiles behave much like the thrown baseball. Specifically, the vertical motion is described by free fall, resulting in constant downward acceleration. The horizontal motion is described by constant velocity. The horizontal and vertical motions combine to produce a curving path known as a parabola. And most importantly, the horizontal and vertical motions do not affect each other. It is also important to note that these traits describe ideal projectiles. Now consider the ideal path of a human cannonball at the circus. Note that the firing angle is upward at about 45 degrees. Is the human cannonball in free fall immediately after the cannon fires? Yes or no? The correct answer is yes. The human cannonball is in free fall immediately after the cannon fires. In fact, the human cannonball is in free fall at all times during flight. Free fall also explains why the human cannonball reaches a peak height and then falls back to Earth. Let's watch the stunt again, this time looking at the horizontal and vertical components of the velocity vector. Note that the vertical velocity component decreases on the way up, is zero at peak height, and becomes increasingly negative on the way down. The constantly changing vertical velocity component is due to the constant downward acceleration of free fall. Note 2, the symmetry of the motion. Moving away from the peak in each direction, the vertical velocity vector components are equal in size, but point in opposite directions. If we look at the horizontal velocity components along the trajectory, we see that they do not change. Because the force due to gravity acts only in the vertical direction, the horizontal motion of the human cannonball is described by constant velocity. Okay, let's recap the key aspects of projectile motion. We set out to describe the motion at key points along a projectile's path, and explain why projectile paths are parabolic. Let's list what we know about the motion along the trajectory. We know that the horizontal component of velocity is constant, that the vertical component of velocity constantly changes and is zero at the peak, and that the projectile is in free fall at all times. We also know that projectiles follow parabolic paths because they are constantly accelerating in the vertical direction while traveling at constant velocity in the horizontal direction.